So today we're going to start with unsupervised learning. Back again to what we were heading for in this first course. We were heading for 6 types of machine learning algorithms. Last time we did the anomaly detection for predictive maintenance on time series, or I'll give an introduction in time series analysis. We have had the risk analysis for decision trees, with decision trees. We did the spam filters with naive Bayes. And today we're going to focus on identifying user types within clusters, so cluster analysis for customer types. And we're going to take a look at the unsupervised idea of machine learning. And next time we're going to do the product recommendation systems or neural networks for pattern analysis. I asked Yusuf whether he could give another lecture, but he wasn't available for next time, so maybe we do an extra session with Yusuf and try to make a lecture on this subject, product recommendation systems, because it's the business side of data science. It's very interesting ideas. So before we get started into this unsupervised learning, let's take a look at machine learning. And this is a picture that you might have seen on internet or even in the thesis of students. So there's a kind of a cheat sheet for which kind of algorithm to choose if you're going to do some neural machine learning in your thesis. And it starts with the question, what are you going to do? What's your goal? And what's your data that you have? So is it your idea to do some dimension reduction? And we're going to get a grip on dimension reduction in a few slides. Do you have responses like labels? Do you have the answer to a question for your part of a data set, like the Titanic set? Do you know for a part of the data set whether people survived or not? Is it labeled data? Are you doing some classification? You want to have a separate discrete number of classes? Or are you going to do some regression, so the continuous learning? And this part below here, this is the supervised part. And why is it supervised? Supervised learning says we have a label, an answer for part of the data, and based on this answer, we want to make a prediction algorithm that classifies or gives values to new data that doesn't have this specific label or answer.
So part of the answers are known.
Part of the answers are known, which is the supervised idea. Part of the data set is known. And then you get the question, is it numeric data you want to predict? Yes or no. You can, for example, you can predict numeric based on numeric, like regression. I got an x value and a y value, which is linear regression is a kind of machine learning, and machine learning is the big AI typical. If you do machine learning, you get a grant. Well, yes, but don't forget that there are simple types of machine learning algorithms that they're still machine learning, and we often use, like linear regression. So we're going to do a regression. Linear regression is here on the slide as well. If you got a predicted numbering, so like we're going to classify, not going to classify, but a regression. What kind of algorithms can you choose? Well, linear regression. We talked about linear regression before. Decision trees, of which we talked about before. Then, of course, the random forest, which is a bootstrapped aggregation of one decision tree. Gradient boosted tree, a version of a bootstrap aggregation, and a neural network. If you want to predict a class, then the question, what kind of class would you like to predict? And what kind of data do you have? Is it, when I want to do a real-time algorithm that's very fast, then support vector machine, SVM, is a very fast algorithm that works flawlessly on several types of data depending on the kernel you use. And the kernel you have seen in one slide of Yusuf, but today we're going to see some kernels as well. if you're going to do explainable data, decision trees, logistic regression, if you've got a large data set, like the spam-ham filter, then naive Bayes, and if it's not large, then linear SVM or naive Bayes. This is all supervised learning. Then there's the unsupervised learning. And this is about, we don't have labels. So we cannot predict anything because we don't know anything, but we do want to see patterns in the data. And what kind of patterns can we extract from data? Well, on one hand, we can ask ourselves, is there a pattern in the data between the types of variables that we have? A very simple example is if you have a data set like this, and you have a, let's say, a user and a temperature in Celsius and a temperature in Kelvin. All of you would say, okay, hey, but these two columns are related. These two columns are the same. But if you have the pressure and the volume, then we can even make more predictions of underlying data. So dimension reduction in this case means we're going to take a look at the data set, and we're going to take a look not at the classes like the labels that we have here, the Y labels, but can we reduce the number of features that we have in our data set? Is there a correlation or a linear or nonlinear relation between one or two columns, and can we from this data set reduce the number of features such that if we do an analysis, we don't measure 2 times the same thing? Because if you're going to do linear regression on this data set, and imagine that now you have temperature in Kelvin and Celsius, so everybody knows, oh, this is double. But if you have 200 measures of an inquiry or a survey, there could be questions that are related to each other. If you do a linear regression on questions that are related, you get answers that are related. And from there, the point is that if you linear regression, you get an overfit or an underfit of these these variables that are related. And this gives you very poor prediction results. So in this case, when we reduce the number of features to the minimum size that tells the story of the whole data set. So this is dimension reduction. And you get principal component analysis, and we're going to do the principal component analysis today. Well, this is latent Dirichlet analysis. We will not touch the Dirichlet distribution today, even not tomorrow. Keep your hands off Dirichlet. It's far too complex. What we're going to do as well is, you can imagine that if you have the other way around, so this is the number of features, but you can also do a dimension reduction in the number of rows that you have. For example, if you have the idea, let's say this is not about temperatures, but about people, like burger service number, and age, income, and let's say intelligence, and postal code. You can imagine that within this data set, there might be people that have similar characteristics. So similar that if we look from a higher level, we say, now these clients, customers are so similar that we can reduce this data set of 16 million football coaches to at maximum 10,000 different types of opinions or different types of users. So we're creating labels by reducing the total size of the data frame. We create groups of users that are closely related within the group, but different from people out of the group. And this enables us to label these groups. And from the labeling, we can say, for example, for a marketing campaign, we're going to target a specific group because the group allows us to do specific, well, marketing instruments, or has a specific probability of agreeing with an offer, or whatever you would like to research. So this type of unsupervised learning is dimension reduction, reducing the amount of variables. This type of machine learning is clustering, reducing the amount of rows. And you can even combine those two. At the end of the day, we will combine those two in one algorithm. And why would you like to do it? Well, if you have 1 billion rows here and 1 million columns there, you get a lot of storage. But if there's a lot of overlapping features and overlapping groups, you might be able to, without reducing the total information too much, reduce the whole data set to far little space. So, unsupervised learning is about the hidden structures of data sets from unlabeled data. So we're not going to talk about the label of the data. We're going to create labels. This means, remember from the previous lectures, that there's no such thing as accuracy or prediction of the model. You cannot measure the quality of the outcome, or measure it in a very difficult way, because you don't know whether the result is good, is valid, because there's no label that tells you whether it's valid. It's a difficult problem with, for example, cluster analysis. So the Y is not available, like spam or ham. And because there's no Y, there's also no such thing as a true positive or a false negative. Because we don't know the label. So we have to come up with different measures, and at the end of the lecture I'll explain you some different measures that enable you to check whether what you've done is really valid. Two types, dimension reduction and cluster analysis. Dimension reduction is about information theory and about the process of reducing your variables to a little set of variables. Next, there's also like anomaly detection, like what you did last time with your time series. It's also a form of unsupervised learning. Why? Because you don't know what the anomaly is beforehand. As soon as you know what the anomaly has of kind of properties, then you're able to label it and to look back into new data. What are the properties of the anomalies, and can I classify a new data set according to the old data set? Yeah? And cluster analysis. Now, some examples. A lot of usage in these. Well, these are two. This is a very, very simple data set with a Y value and X value. And what you can see here is clusters of customer types. Each point is a customer based on its features, and you're within the data set you identify several types of groups of clusters that enable you to do specific marketing analysis. But also very interesting, this idea of density-based clustering. And density-based clustering is about detection of patterns within a picture, for example, and a picture is no more or less than a set of values with color values. So what you can do with, for example, dB scan, it's a density-based clustering, you can detect where the edges of an object are. And you can, from there, you can say, okay, these are the edges of an object, and you're able to detect, for example, walking people or driving cars, because these are the new edges in the overlaying pictures of two subsequent pictures. Or, taken with my own camera, counting of people in a room. Your head is the the most warm element of your body. So if you count the heads in a room by, for example, dB scan, you're able to very quickly count the number of people in a room. Hey, Sharaf. Another idea, I'm not going to show you the video, is of unsupervised learning is factor analysis. Has anyone of you already used factor analysis? No? What you can do with factor analysis, if let's say, for example, you have a lot of features, let's say 100 features, based on a survey, and this survey is divided in different types of questions. Questions about your age, questions about your social status, questions about your income, your intelligence, your physical situation, your mood. From there you can say, hey, I got types of questions, types of elements, and that could be that if these are the questions, and if I expect a type of underlying factors influencing these typical answers, then you can do a dimension reduction methods like factor analysis that enables you to find the underlying patterns between the variables based on kind of an aggregate level variable. Like here is income and postal code and your intelligence. These three could be related to one social status or social class. These relate to where you live, what's your intelligence and your income, and maybe your health and weight and length relate to health consciousness, for example. If you define these, if you want to know how these underlying patterns of influencing variables that are not observed in the data are present, then you can do a factor analysis. And a factor analysis reduces your whole data set to these factors and looks, okay, how do these factors, underlying factors, influence the observed data? Yeah?
Is that also dimension reduction?
Yeah, that's dimension, because these are
It's not in the schedule. It's not in the cheat sheet.
Is it in the cheat sheet? I don't know. Good question. It is a kind of principal component analysis. Principal component analysis and factor analysis are closely related, and the factor analysis is orthogonal to the principal component analysis. But I'll show you the principal component analysis, and I'll explain you what factor analysis is. But they are closely related. They are all. Some people say, but that's not true, that the principal component analysis is a dimension reduction method on one factor. Because you say they're all related. But that's not true. If you want to know more, I got a link to a movie from Ben Lampert, who is a professor or a PD at University of Cambridge, and he clearly explains what factor analysis is. This is also very interesting. This is also a dimension reduction method. It's unsupervised. It's from Sascha Epskamp. It's a colleague PhD student of computational science of mine. And what he does is he does computational psychology. He has a lot of questionnaires, longitudinal, for people about their how they feel. Like I'm indifferent to other one's feelings. I love children. I don't talk a lot, I get irritated, all kinds of classes of questions. And what he makes is a network of how these answers within the classes relate. And from there you can tweak the network and aggregate the network and look how to influence, so to influence people's mood based on the relations that you have between the observed variables. So what you say is there's, instead of saying there's a correlation, you say no, there's not only one correlation, there's a whole correlation network of how people feel. And if you want to tweak people positive in their behavior, you have to find a point in the network where you can positively influence and have a, if you positively influence this one, you get a strong correlation with this one and this one, negative in this case, positive with this case. So you can set the behandeling, the treatment of people. In psychologists can accommodate on the personal network of a person to get the best treatment, psychological treatment for patients, which is far more effective than doing a general treatment. This is also unsupervised learning. You don't know what's in the network before you. There's also no real labeled class. Yeah, so there's unsupervised learning. Now, how can you use these unsupervised methods? Now, for example, we have currently run a project. One of my students at Mr. Green. It's a leasing company for electric vehicles, and what they have is they don't know about their clients, what types of clients there are. But they do want to know if there's similar user types in my whole portfolio of clients. Can I target these people to make them the best offers for customer churn? So to renew their contract, renew their leasing contract. Yeah. So can I set, based on my data and based on the classes within my whole portfolio of clients, specify these high potential user groups. So what they now do is they find patterns. They find the patterns. From there they say, okay, we build a model. We say these are the properties of a user that are typically this kind of user. When a new customer comes in, it gets classified according to the patterns already in the system. And from there you can say, okay, this is this type of user based on my own clients. We're going to make him this offer. So you can, from the labels you get from the unsupervised learning, you can do supervised learning again on new data. Is that clear? A bit? And this is how you can iterate this continuously in your data set. So that's about what is supervised learning. I thought it would be good today to, from the next part of this lecture, I'll give at maximum 3 slides and then an exercise. So your first exercise is to choose a data set. And there are 2 suggestions. There's a cluster datasets package in R, and there's a collection of clusterable datasets on this link. And what you should do is choose first for yourself which dataset you would like to analyze during the rest of this lecture. Choose a dataset that has at least 20 features and at least 2 times the number of items, because otherwise clustering will be very difficult. And do some first analysis of your dataset. So like basic analysis, str function, glimpse, draw a summary, show the first rows, make some plots, and use the pairs function. Yeah. Choose the dataset. You may work together with 1 or 2 persons. Choose the dataset, and we'll use this dataset for the rest of this lecture. Yeah. Let's say maximum 10 minutes. Should be possible.